place to be.
Yeah.
Let me just make you co-host. Here we go. What are you doing, Abby? I just saw you in the corner of my eye. I'm like, what's going on there?
I thought nobody noticed, so I'm my virtual hair.
Didn't see a thing.
Hello.
Right. Here we go. That's a busy morning. Right. Wow, what a shirt meet.
Nice. It really reminds me of chess. I should have made some chess jokes.
All right.
It suits you well.
Thank you. I hope your chessboard is not like this.
Yeah, it's for occipital activations.
That's right. Or after psychedelic drugs.
Yes.
Right. Welcome to Neuroccino, everyone. It's 9:30 on this Monday morning. Today we have a paper called the Connectome-based machine learning models are vulnerable to subtle data manipulations. And Patrick kindly volunteered to present today. Just FYI, next week is a bank holiday, so there won't be a Neuroccino next week. Recap of the rules. Anyone is welcome to present any type of science they read and thought was exciting. So just come on and tell us why you thought it was exciting, except for your own work, which we all know is always the most exciting. Without further ado, Patrick, if you want to share your screen, I already shared the link with everyone.
Yes, so I'm taking over and let's start a bit more unconventional. Well, we all have an impression of machine learning, right? We know what machine learning could do or have some ideas about what machine learning can do. And there are a lot of memes, right? One could go so far to really ask if ChatGPT, for instance, might be the new Lord and Savior of science and of easier stuff to compute. So one thing that might sometimes be overlooked is that even machine learning can be subject of severe data manipulation. And that's what we're talking about today. So this paper came recently out from Rosenblatt et al. That's the Dustin Chinos group. Just recently came out in Patterns and has this very provocative title: Connectome-based machine learning models are vulnerable to subtle data manipulation. You can already see here from the graphical abstract, I can increase size, that one of the core issues may be that with certain types of manipulation, there might not be a clear difference between manipulated and real data. And that's basically what we're talking about. So in general, there is quite a push in machine learning to increase what can be called, sorry for that, trustworthiness. In this paper, trustworthiness is defined as the robustness to data manipulation. And we try to create, in general, machine learning algorithms that are robust against certain biases, such as fairness biases, including race biases, gender biases. But what about biases against voluntary manipulations? How easy is it to really manipulate the data? This is the core issue about trustworthiness, or how they define it, robustness to data manipulation. In this study, they looked at two different types of manipulations. At one point, what they call performance enhancement attacks. This is basically voluntarily changing the sample, the core data set or the main data set, the whole data set, to create relationships that might not be there. Or the other part is attacks such as adversarial noise, which means we increase noise in the data to hinder the model to learn some relationships and decrease prediction. So basically, performance enhancement increases prediction, and adversarial noise decreases prediction. So what did they do? They looked into 4 different data sets: the ABC study, the HCP data set, PNC, and a clinical relevant data set, which is the SLIM data set. From the first 3, they aimed to predict IQ and self-reported sex. And from the SLIM data set, they aimed to classify people as either state, with regards to state anxiety. So in order to create a baseline model, they first used a rich regression model to predict fluid intelligence. So for those who are, let's say, a bit more unfamiliar to machine learning, what you typically do is you have your data, which is here on the top right. Let me increase the size again. So you got your data, you acquired the data, you then obviously do some pre-processing and parcellation. At some point, like people argue when is the right point, you split the data to a training data set and a test sample or test data set. And you train the machine learning algorithm on the training data set and test its performance or generalization ability on the test data set. That's typically done using a cross-validation approach. So let's say we've got our data. We pre-processed the data, we got the signal out of it, we parcellated the brain into different modules or different regions of interest. From there, we constructed the functional connectomes on which we then trained the data to predict a variable or classify the data points with regards to, for instance, sex or mental health status. And at various points, you can already include some data manipulations. For the pre-processing, for instance, you can work on time series enhancements. So you add some information or you add some variance that is correlated with the variable of interest, let's say with IQ, or you can do this on a connectome level. Or when you test your model, you can decrease performance using adversarial noise attacks. So this is basically the pipeline that they tested. Okay, how did they do this noise, the enhancements? They basically, for connectome enhancements, shows randomly selected 20% of randomly selected edges across all participants. And they added individual specific patterns that were, as I said, correlated with the variable of interest, for instance, IQ or fluid intelligence. And what they found was that not only did they achieve a really, really high near perfect correlation, which you can see here on the right. This is basically the result figure for the main pipeline for performance enhancements, where you can see, depending on how much you scale it, you can get really, really strong correlations between the predicted measurement. So this is what the machine learning algorithm would give us out, and the actual real measured IQ. So it goes up from no correlation in the original data set with 0.18 of a correlation coefficient to super high correlation coefficient with 0.97. And unfortunately, the edgewise correlations between the original data set and the enhanced data set or manipulated data set is super high with 0.99. So we can't really find whether or not data has been manipulated or not in this case. You can also check other things. So they checked whether or not such enhancement of the data or such manipulation for IQ now would have an effect on other downstream analysis. For instance, when it comes to identifying individuals, we typically use the fingerprinting approach by Finn, where we are looking at whether or not, or to what extent the connectome can be linked back to an individual. And to be honest, no such luck. I think fingerprinting was, I'll need to find it, but spoiler alert, fingerprinting shows same results. I go over some different other things that they looked at. For instance, enhanced data, IQ enhanced data, has also no effect on sex classification accuracy. So regardless of the analysis they looked at, such as identification, correlation between original data and enhanced data, sex classification using the enhanced data, comparing the original version and the enhanced version, as well as looking at several graph properties. None of this really identified the enhanced data as modified data. Okay, so that's not the best thing to hear, obviously. It's also quite clear when we look at here in the top left. Not sure how good this can be seen actually. Here on the top left, the original data now distributed into subnetworks. These are the geo networks, and the enhanced data. There's nearly no visual difference between the two. So it's really, really hard to identify modified data. And modified data still has a huge impact, as we've seen from the numbers. Similarly, I'm not super happy with my, right, we do this differently. Okay. So this is what we've talked about so far. No difference. Performance enhancement really has a huge effect with minor changes to the connectomes. And the same can be said in the clinical setting, where they use enhancement to basically increase the prediction of measured state anxiety. I think they don't have pictures for it, but we talked about this adversarial noise decreasing performance. And here we can decrease performance to near zero or zero accuracy. And still, there's no apparent visual difference between the real and corrupted connectomes, which obviously means there are huge issues. So how could we possibly solve this? One thing that they thought about was, instead of, or basically suggesting researchers to always publish the raw data as well, which would make sense, right? if you corrupt the connectomes, which is a downstream analysis, you haven't corrupted the original data, and then we could potentially see whether or not data has been corrupted using the raw data. But there's no such luck, because what they also looked at is whether or not we can just increase performance on the time series directly. So this is what they did. They enhanced time series, or the relationship on the raw data, basically, with the phenotype of interest. And still, the resulting connectomes look super similar. So there's no real difference between the original connectome that results from the not enhanced time series from the original, and the enhanced connectomes, which comes from the enhanced or manipulated time series. And still there's a huge effect on the accuracy of the machine learning algorithm. So on the left, you see basically no correlation between the assumed predicted IQ and the real IQ. But on the right, there's a strong correlation with the manipulated data of 0.77. Okay. So what can we do in the end? Obviously, this paper shows something that is not, let's say, super surprising. If we are clever about manipulating data, we can. And even the fancy machine learning algorithms are not capable of solving this issue. So not by themselves, basically. This is not the surprising part for me. What is kind of surprising is that with the analysis they did, we couldn't find differences between the original data and the corrupted data. So some things that they mentioned which might increase our trustworthiness as researchers using algorithms is either using data provenance tracking tools, such as data-led or blockchains. So for those who don't know, data-led is a platform that's developed basically in our institute at Research Center Jülich, where the aim is to provide ways to replicate and reproduce data using code or processing steps as well, using a code which is then version controlled. And similarly, blockchains can just tell us where data is coming from and how it has been manipulated. And the second thing that is arguably even more practical is to generalize the models. So basically test the models with external data sets, because not all data sets should be manipulated, hopefully. So I think I end it here. Thus, we have 10 minutes approximately to discuss some more. But I really, well, like this paper, despite the, let's say, negative message and somewhat unsurprising message that a mean, evil scientist can still manipulate data. All right.
Thanks.
Any questions?
You probably didn't see this, but there was tons of questions already in the chat, and Chris already has his hand up. So you definitely hit a nerve here. Some of the questions I think were answered along the way. For example, the was it leaf one out data design? I think you just answered that with generalizing.
Yes, so not leave one out, but tenfold cross-validation.
There we go. Okay, let's go with the order of hands. So Chris, you go first.
Hi, thank you for this paper. It's very interesting. One thing about the solutions. So yeah, I was thinking generalization on external data set. That's an obvious thing, but of course it's difficult, especially with the clinical populations and stuff, because it's not that easy to have another data set big enough for machine learning in another like another 2000 images or something like that. That's difficult. But I think one other potential solution that would require changes in how we publish papers and how we make science, essentially, it would be to have open data sets. So, of course, it's difficult with clinical data, for example. But if the open data set is available and fixed, of course, and then you publish the model, you can't really, if someone was trying to reproduce your findings, so with the model published and the open data set, I don't see how, if it's done properly, I don't see how you could fudge the data. What do you think about
it? Yeah, I think, yeah. I mean, I don't want to underestimate the evil of humans that want to manipulate things, right? So it's also one of the things we're talking here about, trustworthiness of the machine learning algorithm, in the sense that they defined it. There are other types of or ways to define trustworthiness. And in the end, they discussed, or in the discussion section, they wrote about whether or not we can trust data, or sorry, I don't want to incorrectly paraphrase them. I'm just searching for it.
I mean, there would always be a way to cheat. I mean,
yes.
Humans are very good at that, especially with incentives. So in the end, of course, there will always be some part of trust, and the only thing that will eventually find bad results will be replication with external data, I think.
Yes.
Yeah,
I think so too. Like, obviously, replication studies are a necessity, and I think it's not really a new thing, right? Because the same argument can be made for statistics. It's not like this is exclusively an issue for machine learning. On the contrary, like, we know about that in conventional statistical research, experimental research, for a long time. So it's not like they reinvented the wheel and showed something different. I also talked with our machine learning leader at the Institute, who was a bit surprised that this paper even came out, because what they're hitting at is so obvious in a way, right? But I still think it's really important to get the message clear for, especially, let's say, some minor researchers, or some, not even researchers, but for people out there. Like, I showed all the memes at the beginning, right? That people that basically believe whatever the algorithm tells me is correct, right?
I don't think that's superficial to show that, because so many researchers and so many people are using machine learning without understanding the inside. I mean, I'm using machine learning, and there are so many things I don't know about machine learning, and so many mistakes I could even do without noticing.
You're right. Definitely. I agree. Yeah.
I would also agree that sometimes it's very obvious to people in the field, but sometimes you need a paper that just states the obvious. So yeah. Mish, you have your hand up.
Yeah, sorry about
Don't
this.
hide your belly. Come on.
I lost a bet, and I have to do it. This is
At some point you
actually
need to.
It's a young investigator Wiley OHPM award.
Hang on, young investigator.
Yeah, no. So the story is, I have the belt because Hiroyamasa Takemura, who was the Young Investigator Award last year, couldn't bring it to Montreal. this year. So he came from Japan and dropped it in my office. And I have to bring it to Montreal in July. Then I lost his pet and I have to wear it during Neuroccino.
Don't you think it's good content to reveal what the bet was?
Transparency. We can't trust you unless you reveal. No.
I honestly don't remember what was the bet about. I just remember that.
Kudos for you, though, to honoring losing your bet.
I always honor my losing bet. That's what I do.
Is this a one-off, or is this going to be a recurrent Neuroccino
No,
thing
it's just
until
like,
we go to Montreal?
It's a one-time thing for me.
All right, fire away. What's your question?
So anyway, what's the question? So yeah, it is something that is pretty much well known, that you should validate data out of sample completely. Recently, I did this analysis using backward stepwise linear regression, which is, you know, pretty simple statistical model predicting my data, and I could explain 30% of the variance, which is quite all right. But then I was like, oh, let's try to scramble the data and try to predict noise. And there I could predict 20% of the variance of the noise with the same variables. So that's R squared of 0.2, which I was like very surprised. But then like the good thing is when you bring it out of sample, obviously you get 0 for the noise, and you still keep like 0.25, 27 for the real data. And that's even the simple model. I mean, like, as you say, it's statistically general. It's necessary to have out of sample validation of the prediction. Then it's different if you want to do statistical association.
It's basically akin to replication, right? When or one could at least look at it like that.
But now Nature Publishing Group, they have in their like editorial report, like you have to submit some document with your paper, and they always ask you what was your strategy to replicate your findings. So if you want to publish in these kind of journals and be in good time with the editor, always thinking ahead and think about having a way to answer that question, like I replicated doing this or doing that. And then so you don't find it by surprise and actually say, no, we didn't replicate. But thank you. That was really good.
You're welcome. Sure.
Are there any other questions? I know there were more in the chat. Were they answered? Do you still want to?
Just a comment, maybe. Just thinking about what Chris and Pat was saying, that it's interesting to see that we had this history of fighting bias, and one of the bias was data-driven and hypothesis-driven. So one way to solve this issue was machine learning and these things, and it's interesting to see that human nature is always fighting it and trying to find a way to try to find another way to find results, even if it is not just.
I think that's an important word of warning, right?
Yeah.
And yeah, obviously, I don't know of any researchers that would do such things. But then again,
yeah, you never know.
You never know, right?
But yeah, so but yeah, it was interesting also to see that even if you put cross guards everywhere, there is always a way, because I was saying, yeah, if you share everything, so open science is a way to solve that in the way, if you share raw data, pre-processing, and everything, you should be able to fight this. But there is, yeah, if you don't share the proper raw data, if you, yeah, it's there is always a way.
So I guess we just need to stay keen, replicate,
yeah,
use external data sets to generalize,
yeah,
use things like data-led, maybe blockchain, maybe other solutions to try and overcome the potency of cheating.
That cherry note, it's 10 o'clock.
But let's put it that way. I think there are still more good in researchers or more researchers that wouldn't want to do that, and that's why it's important to know about possibilities to, or the falsibility and compromise trustworthiness of data or of machine learning algorithms and methods, so that we can prevent falling into pitfalls and probably uncover things that should be uncovered.
Thank you very much, Patrick, for presenting that paper. Remember, next week is a bank holiday, so no Neuroccino. The week after, let me know if you come across some exciting science that you do want to present. And other than that, I wish you an exciting week in science and see you in 2 weeks. Bye.
Bye.